Welcome to this educational presentation on ionic bonding, formation, and properties. Ionic bonding is one of the fundamental types of chemical bonds, where atoms transfer electrons to form positive and negative ions. These oppositely charged ions are then held together by powerful electrostatic forces. From table salt to the calcium phosphate in our bones, ionic compounds are everywhere. In this presentation, we will explore how ionic bonds form through electron transfer, the crystal structures they create, and the unique properties that result. Electron transfer is the heart of ionic bonding. Atoms with low ionization energy, typically metals on the left side of the periodic table, readily lose valence electrons to form positive cations. Atoms with high electron affinity, typically nonmetals on the right side, eagerly accept those electrons to form negative anions. Consider sodium and chlorine. Sodium has one valence electron and a low ionization energy of only 496 kilojoules per mole. It readily loses its 3s electron to become Na+, which is isoelectronic with neon. Chlorine has 7 valence electrons and a high electron affinity of minus 349 kilojoules per mole, accepting an electron to become Cl-, isoelectronic with argon. The oppositely charged ions attract each other via Coulomb's law. The octet rule is the driving force behind ion formation. Atoms tend to gain, lose, or share electrons to achieve a stable configuration of 8 valence electrons, matching the electron configuration of a noble gas. Sodium loses its 1 valence electron to achieve the neon configuration with a 2s22p6 arrangement. Chlorine gains 1 electron to achieve the argon configuration with 3s23p6. This rule explains common ion charges. Group 1 metals form +1 cations. Group 2 form +2. Group 16 nonmetals form -2 anions, and Group 17 halogens form -1 anions. Transition metals can form multiple charges like iron 2+ and iron 3+ due to their d orbital electrons. The completed octet creates a lower energy state that makes bond formation energetically favorable. Ionic compounds do not form discrete molecules. Instead, they arrange themselves into vast three-dimensional crystal lattices where each cation is surrounded by anions and vice versa. The sodium chloride structure is known as the rock salt structure. Each sodium ion is surrounded by 6 chloride ions at the vertices of an octahedron, giving a coordination number of 6. The repeating unit is a face-centered cubic arrangement. Other common structures include the cesium chloride structure with coordination number 8 for larger cations and the fluoride structure for compounds with 2-to-1 stoichiometry. The specific structure depends on the relative sizes of the ions, known as the radius ratio rule, and their charges. Lattice energy is the energy released when gaseous ions come together to form 1 mole of an ionic solid. It is a direct measure of the strength of ionic bonding in a crystal. The higher the lattice energy, the stronger the ionic bond, and the more stable the compound. Lattice energy depends on 2 main factors. First, the charges of the ions. Higher charges produce much stronger attraction. Second, the sizes of the ions. Smaller ions allow closer approach and stronger attraction. For example, magnesium oxide has a lattice energy of minus 3,795 kilojoules per mole compared to sodium chloride's minus 787. That is nearly 5 times larger because magnesium 2+ and oxygen 2- have double the charge of sodium plus and chloride minus. Lattice energy explains trends in melting points, hardness, and solubility. Lattice energy cannot be measured directly. The Born Haber cycle provides an ingenious indirect method using Hess's law. For sodium chloride formation, we construct a thermodynamic cycle. First, sublimation of solid sodium to gaseous sodium requires +108 kilojoules per mole. Second, ionization of gaseous sodium to sodium plus requires +496 kilojoules per mole. Third, dissociation of chlorine gas into chlorine atoms requires +122 kilojoules per mole. Fourth, electron attachment to chlorine to form chloride releases -349 kilojoules per mole. And fifth, The unknown lattice energy completes the cycle. The sum equals the enthalpy of formation of sodium chloride, which is minus 411 kilojoules per mole. Solving for lattice energy gives minus 787 kilojoules per mole. This cycle beautifully demonstrates how the favorable lattice energy overcomes the unfavorable costs. Ionic compounds have remarkably high melting and boiling points because of the strong electrostatic forces holding the crystal lattice together. To melt an ionic solid, enough energy must be supplied to overcome these forces and allow the ions to move past each other. Sodium chloride melts at 801 degrees Celsius and boils at 1465 degrees. Magnesium oxide, with its double-charged magnesium and oxygen ions, melts at 2852 degrees Celsius, hot enough to be used as a refractory material in furnace linings. The trend in melting points follows lattice energy. Higher lattice energy means higher melting point. Compounds with small, highly charged ions have the highest melting points. This property makes ionic compounds useful in high-temperature applications, from ceramic insulators to industrial furnace linings. Ionic compounds do not conduct electricity in the solid state because the ions are locked in fixed positions within the crystal lattice. They cannot move to carry charge. However, when melted or dissolved in water, the ions become free to move, and the liquid or solution becomes an excellent conductor of electricity. This is the principle behind electrolysis, where passing an electric current through a molten ionic compound causes chemical decomposition. For example, molten sodium chloride conducts electricity with sodium ions migrating to the negative electrode, where they gain electrons to form sodium metal, and chloride ions migrating to the positive electrode, where they lose electrons to form chlorine gas. This conductivity behavior is a key test to distinguish ionic compounds from covalent compounds. Most ionic compounds are soluble in polar solvents like water because the strong dipole of water molecules can overcome the electrostatic attraction between ions. Water molecules surround each ion in a process called hydration, and the energy released compensates for the lattice energy that must be overcome. The solubility of an ionic compound depends on the balance between lattice energy and hydration energy. Compounds dissolve when hydration energy exceeds lattice energy. Ionic compounds are also typically hard but brittle. When you strike an ionic crystal, the force can shift one layer of ions relative to another, bringing ions of like charge next to each other. The resulting electrostatic repulsion causes the crystal to shatter along specific planes. This brittleness is a defining characteristic. Bojon's rules describe when ionic bonding acquires significant covalent character. No bond is purely ionic. There is always some electron sharing. The key factors are small cation size, large anion size, and high charge on either ion. Small cations like lithium plus have high charge density and strongly distort the electron cloud of the anion. Large anions like iodide have diffuse, easily polarizable electron clouds. Cations with charges of 2 plus or 3 plus, like beryllium 2 plus or aluminum 3 plus, strongly polarize anions. For example, lithium iodide is less ionic than lithium fluoride because iodide is much larger and more polarizable than fluoride. Aluminum chloride behaves more like a covalent compound despite being composed of a metal and nonmetal. Chemical bonding exists on a spectrum from purely ionic to purely covalent, with polar covalent bonds in between. The key parameter is the electronegativity difference, or delta En. Linus Pauling established that a delta En of 1.7 on his scale corresponds to 50% ionic character. Bonds with delta En greater than 1.7 are considered predominantly ionic, while those with delta En less than 0.4 are predominantly nonpolar covalent. Bonds in the middle range are polar covalent, where electrons are shared but spend more time near the more electronegative atom. For example, NaCl with delta En of 2.1 is about 67% ionic, while HCl with delta En of 0.9 is about 17% ionic and 83% covalent. Not all ions are single atoms. Polyatomic ions are groups of covalently bonded atoms that carry a net electrical charge and participate in ionic bonding as a unit. Common examples include ammonium, NH4+, nitrate, NO3-, sulfate, SO42-, carbonate, CO32-, phosphate, PO43-, and hydroxide, OH-. These ions form ionic compounds with oppositely charged ions. For example, ammonium nitrate NH4NO3 is used as fertilizer, calcium carbonate CaCO3 is found in limestone and eggshells, and sodium phosphate Na3PO4 is used in detergents. The naming follows systematic rules with the cation named first, followed by the anion. This IUPAC system allows chemists worldwide to communicate unambiguously. Quiz question 1. Which of the following best describes the primary force holding an ionic bond together? Option A, sharing of valence electrons between two atoms. Option B, electrostatic attraction between oppositely charged ions. Option C, attraction between positive nuclei and delocalized electrons. Or option D, van der Waals forces between neutral atoms. Take a moment to think about your answer. Quiz question 2. Which compound would you expect to have the highest melting point? Option A, sodium chloride with Na plus and Cl minus. Option B, magnesium oxide with Mg2 plus and O2 minus. Option C, potassium bromide with K plus and Br minus. Or option D, cesium iodide with Cs plus and I minus. Consider how lattice energy affects melting point. Question 3. The large jump between which successive ionization energies of magnesium confirms it has two valence electrons? Option A, between IE1 and IE2. Option B, between IE2 and IE3. Option C, between IE3 and IE4. Option D, between IE4 and IE5. The correct answer is B. Magnesium has the configuration Ne3s2, IE1 at 738 and IE2 at 1450 remove the two 3s valence electrons. IE3 at 7730 is a five-fold jump because it removes an electron from the neon core. This confirms magnesium has exactly two valence electrons. Quiz question 4. According to Fion's rules, which of the following would have the most covalent character? Option A, lithium fluoride with small e plus and small f minus. Option B, lithium iodide with small e plus and large I minus. Option C, potassium fluoride with large K plus and small f minus. Or option D, potassium chloride with large K plus and medium Cl minus. Question 5. What was Thomson's name for the particles he discovered, and what evidence convinced him they were universal constituents of all matter? Thomson called them corpuscles. He found that the E/M ratio was identical regardless of the cathode metal, whether platinum, aluminum, or iron, and the gas in the tube, whether air, hydrogen, or carbon dioxide. This universality proved these particles were fundamental building blocks present in all forms of matter. Now, let us work through some problems. Problem 1. Rank sodium, magnesium, potassium, calcium, and bromine in order of increasing atomic radius. Step 1. Identify the positions. Sodium is group 1, period 3. Magnesium is group 2, period 3. Potassium is group 1, period 4. Calcium is group 2, period 4. Bromine is group 17, period 4. Step 2. Across period 3, magnesium is to the right of sodium, so magnesium is smaller. Step 3. Across period 4, bromine is far to the right of calcium, so bromine is smaller. Step 4. Down group 1, potassium is below sodium, so sodium is smaller than potassium. Step 5. Down group 2, calcium is below magnesium, so magnesium is smaller than calcium. Step 6. The final order from smallest to largest is bromine at 114, magnesium at 150, calcium at 180, sodium at 186, and potassium at 227 picometers. Problem 2. Born Haber cycle calculation. Using the following thermodynamic data, calculate the lattice energy of potassium bromide. Sublimation of potassium plus 89 kilojoules per mole. First ionization of potassium plus 419. Half bond dissociation of bromine plus 112. Electron affinity of bromine minus 325. And enthalpy of formation of KBr minus 394 kilojoules per mole. We will apply the Born Haber cycle. Problem 3. Explain why boron has a lower first ionization energy than beryllium, even though boron has a higher nuclear charge. Step 1. Compare the electron configurations. Beryllium is He2s2. Boron is He2s2, 2p1. Step 2. In beryllium, both valence electrons are in the 2s orbital, lower energy and closer to the nucleus. Step 3. In boron, the outermost electron is in the 2p orbital, higher energy and further on average. Step 4. The 2s electrons shield the 2p electron from the full nuclear charge. Step 5. The effective nuclear charge for beryllium's 2s electron is about 1.7, while for boron's 2p electron it is only about 1.6. Step 6. The 2p electron is easier to remove despite the higher atomic number, because electron configuration matters more than nuclear charge alone. Problem 4. An unknown element in period 3 has a smaller atomic radius than silicon but larger than chlorine. Its first ionization energy is higher than aluminum but lower than silicon. Identify the element. Step 1. Period 3 elements are sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Step 2. Radius between silicon and chlorine narrows it to phosphorus or sulfur. Step 3. Check ionization energy values. Aluminum is 577, silicon is 786, phosphorus is 1060, sulfur is 1000. Step 4. Find the element with IE higher than aluminum, but that fits the radius constraint between silicon and chlorine. Step 5. Both phosphorus and sulfur fit the radius constraint. Phosphorus has IE of 1060, sulfur has IE of 1000. Step 6. The answer is phosphorus. Problem 5. Three group 1 elements have first ionization energies. Lithium at 520, potassium at 419, and an unknown element R at 376 kilojoules per mole. Identify R, determine the strongest reducing agent, and arrange them by increasing atomic radius. Step 1. Group 1 ionization energies decrease as we move down. Lithium is 520, sodium is 496, potassium is 419, rubidium is 403, and cesium is 376. Step 2. 376 matches cesium. R is cesium. Step 3. The strongest reducing agent is the element that loses electrons most easily. Cesium has the lowest IE of all elements at 376, making it the most powerful reducing agent. Step 4. Atomic radius increases down group 1. Lithium at 152, potassium at 227, cesium at 265 picometers. The order of increasing radius is lithium, potassium, cesium. Let us review the key concepts. Atomic radius is the distance from the nucleus to the outermost electron. It decreases across a period and increases down a group. Ionization energy is the energy to remove an electron. It increases across a period and decreases down a group. Both trends are driven by effective nuclear charge. ZF equals Z minus S, and it increases across a period. Exceptions occur when starting a new p subshell, where the p electron is easier to remove than an s electron, and when electron pairing creates repulsion in p4 configurations. Successive ionization energies show dramatic jumps when core electrons must be removed, revealing the number of valence electrons. The largest atoms with the lowest ionization energies are in the bottom left corner, cesium and francium. The smallest atoms with the highest ionization energies are in the top right corner, helium and fluorine. Understanding these trends is essential for mastering all of chemistry, from bonding and reactivity to the design of new materials. Periodic trends are not just abstract numbers on a chart. They are the language atoms use to express their identity. When we see that atomic radius decreases across a period, we are describing how each successive element pulls its electrons closer as the nucleus grows stronger. When we see ionization energy drop down a group, we are witnessing how atoms let go of their outer electrons more easily as they grow larger. These trends explain why cesium explodes in water while helium forms no compounds at all. They explain why fluorine is the most reactive nonmetal, desperately wanting one more electron. They explain the colors of transition metals and why lanthanides are so difficult to separate. The periodic table is more than a chart. It is a conversation between elements, and periodic trends are the grammar that gives it meaning. Thank you for joining us on this journey through the periodic trends of atomic radius and ionization energy.